Guys, what's up?
Okay, so we proceed. So when you have too many structures, okay, when you have too many structures or atoms bonding to another atom, this atom will assume what we call hybrids, or we have resonance hybrids. Simply means there can be an interchange in the bonds, okay? If we have too many possible structures for a single molecule, okay? If you want to draw the structure of the molecule and realize that you can draw it in different forms. So those different forms that you can draw them into will be called resonance. So when you're drawing the Lewis structures or the structures of that single molecule, you always include the resonance hybrids, okay? For example,
Come again on the resonance.
Resonance, okay, when you are drawing the structure of a molecule and you realize that this molecule can exist or can be drawn in different forms representing the same molecule, it means those are resonance hybrids, okay? You're able to draw one molecule in different forms. And every time you're drawing the structure of that molecule, you always include the resonance structures, because that molecule does not exist in one structure only. For example, this structure for NO3, okay? So you find that if you number these oxygen atoms, oxygen number 1, 2, 3, it is possible that the hydrogen bond at some point will be on oxygen number 2, oxygen number 1, or oxygen number 3. So you not only draw one, okay, and include that negative sign. No, you draw all the three, because these are possible structures and possible positions for that double bond.
Okay.
Are we together?
Yes.
Okay. So there is no true double bond. You don't know where the double bond is.
Excuse me, sir, I have a question.
Yes, please.
How do you know that there's a double bond in a molecule? How can you tell?
Okay. So we'll go back to drawing of the Lewis structures. I won't go back to the slide, but I'll explain it here. Remember, the first step is you calculate the total number of valence electrons. Second step is you choose which one will be the central atom. Central atom is one which is least electronegative. Okay. Once you choose the central atom, you go to distributing the electrons. Okay. When you distribute the electrons and later realize that the central atom does not have a noble gas state, or it has not attained 8 valence electrons, the central atom, you start adding double bonds, or you start adding a second line to show a double bond with those atoms surrounding it which have a single atom, single electron, sorry, which is not paired. Have you gotten that?
Yes, sir.
Okay. So after you realize that the central atom does not have 8, then you start including double bonds. But selection of where the double bond will be would depend on which of the atoms around the central atom has a single electron which is not paired. Remember, as you're drawing electrons, you're always pairing them. Okay. All right.
Sir.
Yes, sir.
Yes, sir. How can you tell that you're supposed to put a double bond or a lone pair?
Okay. So let's take, for instance, this nitrogen, right?
Yes.
Okay. How many valence electrons does nitrogen have?
I think 5.
5, sir.
5, right? How many valence
Yes.
electrons does oxygen have?
6.
Okay. So there are 3 oxygens. So we have 18 valence electrons for the oxygen, right? And 5 from the, okay, 5 from the nitrogen. So when we start distributing the bonds, the electrons, we start with giving a single bond to each. So give a single bond on each of the, for each of the oxygens. One single bond here, one single bond there. Okay. So a single bond on each. Then from there, we'll check the central atom. If we put a single bond for each, how many electrons will nitrogen have at the center? It will have 6. It's supposed to have 8, right? So remember from the 24 that you had, okay? From the 23 that you had, 6 of them have been used here, okay? So you are left with 17. Of those 17, you distribute them equally on these 3 oxygen molecules. Now 17 divided by 3 is 6 for each, but one will have 5, isn't it?
Yes.
Yes, because they are all oxygen molecules, so you distribute the remaining electrons equally. So one will have 5. The one that will have 5 will have 2 pairs and 1 lone pair and 1, isn't it?
Yes.
So that 1 electron will indicate a bond coming towards the nitrogen. Remember, the others are 2, 2, 2, 2, 2, 2 on all the 3, all the 2, all the remaining 2. Okay, we had 6 on this oxygen, 6 on this oxygen. So there are 3 pairs here and 3 pairs here. But this oxygen had 5. So there were 2 pairs and 1 single one. So that single one is what will dictate a double bond there. Okay. Are we together?
Yes.
Yes, sir.
Okay. So in order for you to avoid drawing all the 3 structures like this, okay, like the way we've done it up here, you can abbreviate it in this form. Okay. So you can abbreviate it in this form down here, showing that the double bond, so the other line there will be a broken line, showing that the double bond is alternating in those 3 positions. Okay. All right. So now we go to the theory code, which they pronounce as VESPA, but it's actually valence shell electron pair repulsion. So this theory tells us that an electron pair has got a, yes, sir.
Yes, sir. The question, the same resonance structures.
Okay. Yes, sir.
How do you know that this structure may have a resonance and this, I mean, this model can have a resonance structure, or maybe this one or not?
Okay, so when you draw the structure of that molecule, okay? Are you getting that?
Yes, sir.
First, you need to understand how to draw the structure of the molecule. Okay. After you draw the structure of the molecule,
Okay.
then you go to, once you look at the structure of the molecule, for example, our previous molecule here, we were seeing that it is the same atom surrounding the central atom, isn't it?
Yes, sir.
Okay. So it's possible that since it's the same atom surrounding the central atom, it is possible that the double bond can be anywhere, isn't it?
Yes.
Yes. So then you Okay. Then from there, you look at if it's possible that it can be anywhere, simply means those are resonance structures. Okay.
Okay, sir.
Yes. Okay. So you need to have a structure first for you to determine the resonance structure. Okay. Now, VESPA tells us that an electron pair has got a greater repulsion for an unshared electron. A lone pair has got a greater repulsion for shared pairs. Okay. So from this this diagram we're seeing here, this slide we're seeing here, we realize that the electron pairs in the valence shell around the central atom of a molecule repel each other, okay, because they are all negative. So in order to minimize this repulsion, we need to make sure they are further apart from each other, okay? But because there are two types of valence electrons, we have the bond pairs and the lone pairs. The lone pairs have got a greater repulsion than the bond pair. So a lone pair to lone pair repulsion is greater than a lone pair to a bond pair repulsion, and the least repulsion comes from a bond pair to a bond pair. What does this mean? Let's look at a structure. Okay, I'll skip to this. I'll get back to the previous slides so that we understand this. This structure here, the SnCO3, we have 3 pairs of electrons which are shared. Now, between these 3 pairs of electrons which are shared, these have got a less repulsion towards each other. These 3, they do not repel each other that much. But this lone pair will push these 3 away, further away. That is why the structure of the SnCO3 will see the lone pair being further away from the paired ones, from the bonded ones. Okay. Simply means that the lone pair has got a greater repulsion than the bonded pairs. Okay, the bonded pairs, as you can see, are together or are closer to each other. Sorry, that is what our statement means there. Okay, that the lone pair to bond pair here had a greater repulsion than the bond pair to bond pair. Okay. So because of that, it will determine the shape of the molecule. So we predict the shape of the molecule from the number and the type of valence scale electron pairs. So first we needed to have drawn the Lewis structure. Okay, the Lewis structure will tell us which electrons are bonded and which ones are shared, sorry, and which ones are lone pairs. Okay, then from there we ensure that the lone pair, okay, the lone pair will have the greatest distance away from the bonded pairs, or will be further away from the bonded pairs. In this case, we look at the structure of, if we have 2 pairs, or the total number of electron pairs are 2, we're going to have a linear structure. For example, in carbon dioxide, we've seen the bonding in carbon dioxide gives us a linear structure because there are 2 pairs of electrons shared on each side. If we have 3 pairs of electrons shared from the central atom, for example, in this, the bonding between boron and the 3 fluoride atoms, okay? So you will see that the bonding pairs are 3. There are no non-bonding pairs, okay? So there will be even distribution. Okay, there will be an even angle between the bonds because these guys have got an equal repulsive force. But when we have 3 pairs, and of those 3 pairs, only 2 are bonding, there is 1 lone pair. The lone pair will have a greater angle away from the other 2. Are we getting the point here? The lone pair will have a greater repulsion from the bonded pairs. That is what this means. That's why we have a linear, a trigonal planar, and a bent structure. Trigonal planar simply means It's in one plane. But the bent structure pushes the other two away. Okay? There's a lone pair there with a greater repulsive force. Is that clear on the VESPA theory?
Yes, sir.
Any questions?
Very.
Okay, we proceed. Now, if we have 4 pairs, these 4 pairs, there are no, let's start with the one where all the 4 are shared. They are not unshared. They are no lone pairs. So they'll have an equal distance away from each other. So these will be distributed in different planes. This diagram here is showing us these atoms in different planes. The hydrogen atoms are in different planes, bonded to this carbon. But where we have 3 bonding and 1 lone pair, the lone pair will take dominance and push the other 3 in other planes. Okay? Where we have 2 lone pairs, these 2 lone pairs will be further apart from each other and push the other 2 further apart away from them. So the more lone pairs you have, the further the distribution. You even change the structure. The structure changes. This is a bent. This is trigonal pyramidal. So this is in a pyramid form where the lone pair will be at the apex. Then this is tetrahedral in all 4 directions. Okay. All right. More examples. This is the one we looked at earlier as well. Okay. So any questions before we look at hybridization in a few minutes? We only have a few minutes to discuss hybridization. Any questions?
So I have a question. What's the difference between trigonal pyramidal and trigonal planar?
Okay, so we are saying trigonal planar, they are all in one plane. Okay, if it's the X plane, the X plane, the Y plane, Y plane, it's just one plane. They are flat. It is a flat structure. Are you getting that?
Okay.
Then
Yes.
trigonal pyramidal, we have a pyramid. Remember a pyramid has faces, right?
Yes.
Yes. So this dark line, this larger arrow here is representing the one coming closer to you. Okay? The one coming out of
Okay.
the page. Then this one is showing the one going behind there. And this one, this other continuous one is showing the one in the same plane as the page. Are you getting that? So
Yes.
the pyramidal one forms a pyramid. The pyramid has faces and those edges on the pyramid are in different directions. That's what we are saying.
Okay.
Yes. But the trigonal planar is in one plane. Tetrahedral has them in 4 different planes or 4 different directions. Okay.
Okay.
Yes.
Yes.
So again, the key there is the Lewis structure. 1. From the Lewis structure, you need to know the lone pairs. How many lone pairs are there? If there are 2 lone pairs and there are 2 bonded ones, you have a bent structure. If there's 1 lone pair and 3 bonded, you have a trigonal pyramidal, and so on and so forth. Okay. So in a minute, hybridization. Okay. So hybridization happens when we have different energies and shapes. Okay. So it is suitable for pairing electrons to form a chemical bond. Okay. Like the valence bond theory. For example, in a carbon atom which forms 4 single bonds, the valence shell, the S shell, will be combined with the 3 valence p orbitals. Okay. So for those of us who will be together the next time we'll have the chemistry, or in the next session of the chemistry tutorials, we'll discuss hybridization from there. Otherwise, the session is over. Have a good evening. Thank you.
Thank you.
Thank you, sir. Sir, please don't forget to send us the notes.
The slides. Okay, I'll share the slides. as soon as I'm able to share, I'll share the slides. Okay. So you can join other.
Sorry, sir.
Yes, sir.
Sir, what book is this, sir?
So
I think
there are times when you out combine from different sources, and there are times where you fuse in a few things that you know, and there are times where you use a textbook. So you already have the prescribed textbook, but where you get the other slides from is up to you. Whatever helps
all
you
right, thank you,
understand,
sir.
you can use it, but don't go very far away from what you're supposed to learn.
But I think this one is making sense. Summarize.
Sir,
Yes, madam.
are you going to be conducting physical lessons?
I'm not sure as at now. Okay, so your admin will advise. If that happens, well and good. Okay. Okay, thank you. Good evening.